Welcome, physical science students, to the last video of the school year. We are winding down on nuclear chemistry. This is going to be the only video for nuclear chemistry. We're going to cover some things with radioactivity and nuclear reactions and how those things help us and how they can be dangerous and those sorts of things. Okay, now make sure that you guys are getting all your assignments done. Remember that the last day to turn in assignments is May 17th, Sunday, May 17th. Okay, the final will be posted on Thursday. That's the last thing that you guys will have to do for this class. And then after that, we are done. If you want to make sure that you have the grade you want, double check Infinite Campus, double check the things that I've graded. Make sure that I didn't miss something in Teams or something along those lines. If you need any help with any assignments, just let me know and I will help you as soon as I can. Okay, without further ado, let's get into radioactivity and nuclear reactions. Okay, so radioactivity is the very first thing that we're going to talk about. Very, very important for nuclear chemistry. Okay, so now that we're talking about nuclear chemistry, obviously we have to talk about the nucleus, so let's review. Atoms are made up of protons, neutrons, and electrons. Protons are positive, neutrons have no charge, and electrons are negative. The nucleus is only made up of protons and neutrons. The atomic number equals the number of protons, so if I have 12 protons, that tells me that I have a certain element, okay, whichever one is the 12th element. Okay, atoms are usually neutral. They have the same number of protons as they do electrons. Negative electrons are on the outside, are electrically attracted to the positive nucleus on the inside, and they kind of whirl around on the outside of our atom. Okay, so nucleus is tightly packed and very dense. Protons and neutrons weigh a lot more than an electron does. Those are very light. That's why they rotate around our atom very, very, very widely and very loosely. Okay, almost all of the mass of the atom is contained just in the nucleus. Okay, just in the nucleus. You can think of this nucleus versus the size of an atom. The nucleus is the size of a pea sitting in a stadium, which is the size of the atom. Okay, so the nucleus is very, very small, very, very tightly compact. Okay, so we have a thing called the strong force. Okay, so if you imagine in our nucleus, we have protons that are grouped together. And so if you remember back to when we talked about charges, when we talked about magnetism, okay, like things repel each other. So why don't the protons in our nucleus repel each other and therefore we wouldn't have a nucleus? Okay, why are they so close in the nucleus? Okay, so there's two forces at work. Strong force versus electric force. The strong force is what causes protons and neutrons to be attracted to each other. They're very short range, okay, and they are stronger than the electric force that's going to be repelling. Okay, so the electric force is the force that causes protons to repel other protons. This is more of a long range force. Okay, so these protons are so compact that the strong force is much, much stronger than the electric force that's trying to repel these things. All right, so forces in a small nucleus versus a large nucleus. In a small nucleus, there's few protons and few neutrons. They're very close together, held tightly due to the strong force. Few protons means that there's a weak electric force. Okay, so the strong force is greatly outweighing the electric force. So the strong force is keeping these protons together. In a large nucleus, there's lots of protons and neutrons. And as you add more protons, there's going to be more things trying to repel each other. Okay, they're not as close together, about the same strong force as small nucleus. However, many protons increase the stronger electric force. Protons and neutrons held together less tightly in larger nuclei. So, how does that play into radioactivity? Sometimes the strong force is not strong enough to keep the nucleus together. nuclei decay, and then they give off matter and energy known as radiation. Okay, so whenever we give off radiation, that's from some sort of radioactivity. Okay, nuclei with more than 83 protons are radioactive, but we can also have things that are less, depending on the ratio between neutrons and protons. Okay, elements with more than 92 protons don't exist naturally on Earth. These are our synthetic elements, the ones that are made in a lab. When we forced those protons together with a lot of force, and they also produce radioactive elements. So that leads me back to when we talked about isotopes. Okay, so at the very beginning of this quarter, we talked about isotopes. All atoms of the same element have the same number of protons, but sometimes they have different numbers of neutrons. Okay, we can have helium atoms that have 2 protons and 2 neutrons, or we can have a helium atom with 2 protons and 1 neutron, and so on and so forth. Okay, all isotopes of an element have the same number of electrons and same chemical properties. Okay, they only differ in their amount of neutrons. Number of protons and neutrons in the nucleus is known as the mass number, and that was back when you guys had to add the neutrons to protons to get the mass number. For example, helium-4 is right here. It has a mass number of 4, atomic number of 2. That tells me I have 2 protons and 2 neutrons. 2 plus 2 is 4. Okay, so adding these neutrons can cause our nuclei to go from being stable to unstable. Okay, number of neutrons and protons needs to be similar for nucleus to be stable. For small nucleus, less massive, the ratio 1:1 neutrons to protons keeps them stable. Okay, for large nuclei, when the ratio is 3:2, okay, 3 protons to 2 neutrons, then it is also, or I said that backwards, 3 neutrons to 2 protons, that's when it remains stable. Whenever you get outside of these ratios, that is when you're going to start having radioactive elements. So for example, people like to talk about uranium-235 as being unstable because it's radioactive. It's what we use in nuclear power plants and that sort of things. But uranium-232, which is just 3 neutrons off, is stable, whereas uranium-235 is not. Okay, so just that additional 3 neutrons can throw this ratio off and make something radioactive. Okay, so we first discovered radioactivity. Henry Becquerel left uranium salt in a drawer with a photographic plate. Uranium emitted unknown invisible rays. This was the very first knowledge of actual radiation. Okay, radiation is something that we cannot see, but it's something that can be witnessed over time. Marie and Pierre Curie, hopefully you've heard of Madame Curie before. She literally died trying to figure out radioactivity and radiation and how it all works. Madame Curie died of aplastic anemia. She was the first person ever to win a Nobel Prize in both chemistry and physics, because this is, again, linked to both nuclear chemistry. Okay, so we have nuclear that has to do with the nucleus, but it also has to do with particle physics and protons and neutrons and all that stuff and how they interact. She was also the first woman to ever win a Nobel Prize as well. And that was right at the turn of the century, almost in 1900. Okay, so that's basically all we have for radiation. Okay, now where does this radiation come from? It comes from nuclear decay. So what happens is that these elements and these atoms, they are going to decay and emit some form of radiation away, and that's what interacts with other matter. Okay, so let's look at the different types. So when an unstable nucleus decays, particles and energy, nuclear radiation, are emitted from it. There are 3 types. Alpha, which means that it emits a particle, so it's literally losing a piece of its mass. Beta, also giving off a particle. It's also losing a part of its mass. And then there's gamma that emits an electromagnetic wave. So it's not losing its mass, but it is emitting some form of energy in the form of an electromagnetic wave. So let's talk about alpha particles first. So during alpha radiation, an alpha particle is emitted from an atom. Okay, and remember this is a radioactive atom, so it's unstable and it wants to become stable. So in order to do that, it's going to emit an alpha particle. An alpha particle is made up of 2 protons and 2 neutrons, or in other words, it's one of those helium-4 atoms. Okay, so usually it's with something that has a big nucleus, and it wants to get its ratio again back to the 3:2 that we were talking about earlier. So it's going to give off these in order to try to become more stable. Now, sometimes it has to go into a chain reaction of several decays in order to become stable. But for right now, we're just going to talk about alpha decay, and that's losing one particle. Okay, this is the most massive and it has the most electric charge. Okay, so this is the biggest thing that's going to be emitted. When passing through matter, they exert electric force on the electrons, pulling them away from atoms, leaving ions because it's going to pull electrons and leave things positively charged and that sort of thing. Alpha particles lose energy quickly in this process. They are the least penetrating particles, the least dangerous radiation that we have. Beta and gamma are much more powerful. They'll be much more harmful to tissues and matter and that sort of thing. Okay, they can be dangerous if released inside the human body because they can cause cells to not function properly, again, because of that electric force and then pulling atoms away out of those cells. They can mix up things. They're used in smoke detectors. Alpha particles given off that given off that ionize the air, forming a circuit through the electric current. Smoke breaks that circuit, and it basically is what causes the alarm to go off. Okay, so essentially they're constantly being emitted, okay, and it forms a circuit, okay, with the air, electric current, and smoke causes that circuit to break, which is why we get our alarm. Okay, transmutation, this is the process of changing one element to another through nuclear decay. In alpha decay, 2 protons and 2 neutrons are lost, so the new element that you get is always going to be 2 atomic numbers behind. So if you started out with an atom that had an atomic number of 10, once it goes under alpha decay, you now have the element that is the atomic number 8. Okay, so it's always a -2, and it also loses 4 from its mass number. Okay, again, because that's what it's giving off. Okay, so the next one. This is caused by beta particles or beta radiation. Okay, during beta radiation, a beta particle is emitted. This is caused by the weak force. Again, this has to do with the electric forces that are there, and they cause these things to break off from our nucleus. Okay, beta particle is when an electron is emitted when a neutron decays into a proton. So what ends up happening is that sometimes in our nucleus, a neutron decays and becomes a proton. And what you might be thinking is, okay, neutron becoming a proton, well, that's going to add to my atomic number. You're exactly right. It's going to add to your atomic number. It's going to change what kind of element you have. And in this process, an electron is always emitted. Okay, in that process, an electron is always emitted. Transmutation occurs, but the mass number doesn't change, mostly because I'm not gaining or losing any particles in my nucleus. One is just changing from a neutron to a proton. These are much more damaging than alpha particles. They move much faster. However, again, if you looked at alpha particles, they're stopped by a piece of paper. Beta particles can be stopped by aluminum foil. Lastly, we have gamma radiation. This is when electromagnetic waves with high frequency and short wavelength, which means that they have a lot of energy. If you remember back when we talked about energy, okay, and we talked about waves, things that have high frequency and short wavelengths are the ones that bounce back and forth really fast. Okay, so they contain the most energy. This is the most penetrating form of radiation, no mass, no charge, and they travel at the speed of light. So they're traveling incredibly fast. Okay, and they're not carrying any like actual mass with them. It is just penetrating wavelengths. Okay, penetrating waves. Okay, emitted from a nucleus when alpha or beta decay occurs. So it's not the particles that are going to be detrimental, it is the gamma rays that are going to be detrimental when alpha and beta decay occur. They can be stopped by thick blocks of dense material like lead, but cause less damage to human body. They don't create ions, no electric charge, unlike alpha particles. Yeah, but they are, again, the most penetrating form of radiation. Okay, so then finally, we get to nuclear reactions, which kind of encompasses all of it, because we need these to know what radiation is. We need to know how it decays in order for nuclear reactions to occur. Okay, so the first one we're going to talk about is nuclear fission. Okay, the nuclear fission is how nuclear bombs, nuclear power plants operate. Okay, this is how they produce the energy that they do. So I know you may think of bombs, they cause all this devastation and all that sort of thing. Okay, really all that's being released when we drop a nuclear bomb is energy. But it's so much energy that it completely wipes out everything in its path. Okay, so nuclear fission, much stronger way to release energy than with nuclear decay. So this is a form of nuclear decay in a way, but it is a forced nuclear decay. Okay, so we're actually trying to split this atom on purpose rather than just let it decay on its own. Okay, so it's the process of splitting a nucleus into two or more smaller nuclei. Okay, fission literally means to divide things. Okay, it can only occur with large nuclei, which is why we use uranium and plutonium when we make our nuclear bombs and our nuclear power plants. Products include several individual neutrons, and smaller nuclei. Products are less massive afterwards and also gives off an immense amount of energy. A small amount of missing mass is converted to a large amount of energy. If you remember when we talked about energy and we talked about E equals mc squared, that is the equation that Einstein came up with, saying that energy is equal to mass times the speed of light squared. So it's a way to convert mass into energy. And so if you imagine the speed of light squared, really big number. Okay, so no matter how small your mass is, when it gets multiplied by the speed of light squared, it's going to be an incredible amount of energy. And just to give you an idea of how this works, I'll talk about it in a nuclear power plant first. Okay, so basically what happens is just pretend that you have a bunch of these atoms, okay, in these, we'll say these tubes, okay, in these tubes. What happens is they fire a neutron or something in order to break these atoms apart. Okay, so let's say we have a bunch of atoms of uranium sitting in these tubes. You fire a neutron, okay, it breaks the first one, and in doing so, it breaks off a neutron itself, and that breaks off another one, which breaks off another one. It's this huge chain reaction, and the sum of all the energy is what we get as a result. Okay, so one neutron breaks the first atom, that one breaks into 2, which breaks into 4, which breaks into 8, and so on and so on, and it just compounds on itself. Okay, Same thing happens in a nuclear bomb. Okay, when we drop a nuclear bomb, okay, a neutron splits an atom, that atom splits another atom and splits two atoms and splits four atoms, and what we get is an immense amount of energy produced by these chain reactions of nuclear fission. Okay, which is where I go to next. The individual neutrons that are released can hit another nuclei and cause it to split as well. Chain reaction series of repeated fission reactions caused by the release of additional neutrons. Okay, so once one gets split, more neutrons are emitted, which split more atoms, which means more neutrons are emitted, and so on and so forth. If uncontrolled, releases of a ton of energy in an instant, so for example, the bomb we dropped on Hiroshima in World War II, okay, can be devastating. Okay, we didn't really at that time understand completely the devastation that would occur from one of these bombs. We knew that it would be devastating, but not exactly to the terms that it eventually was. There are still places that experience a lot of radiation and are almost inhabitable because of the amount of radiation and how detrimental it can be to matter, which means anything. I mean, our human bodies and that sort of thing. We can and have learned how to control these things and add materials that can absorb neutrons and control these reactions from occurring. Places like nuclear power plants do this, and basically what they do is in those tubes they can put in what they call control rods to kind of control the reactions and keep them from spreading uncontrollably, if that makes sense. You need a critical mass or amount of material required so fission reaction produces only one more fission reaction. Okay, so meaning that at some point you want the fission to stop. Okay, so a critical mass is you want it to go to a certain place and then stop being able to keep fissioning out. Okay, in an uncontrolled situation, that could be, it could take a really long time. In a nuclear power plant, they have it specifically designed to stop at a certain point so that we don't have nuclear meltdowns and that sort of thing. Okay, the other kind of nuclear reaction is fusion, which we talked about in Earth science. If you remember back to freshman year, when we talked about the sun, inside of the sun is where nuclear fusion happens, and that's where we bring two nuclei together to form a new one. Nuclear fusion process of two or more low mass nuclei combining to form a nucleus of larger mass. This releases an incredible amount of energy, even more so than the fission we were talking about with the chain reactions. Nuclei must be moving fast enough to combine, need to overcome the repulsion of positive charges, so they're moving so fast, and this is why it requires so much heat and so much pressure, because you have to force those nuclei to hit each other in order for it to work. High temperature increases kinetic energy, which means nuclei move faster, like on suns and stars, and that's how all of our elements are made in the suns and in our sun and the stars, by bigger and bigger elements being combined through nuclear fusion. Every atom that exists, except for hydrogen, was originally constructed through nuclear fusion. Obviously, hydrogen was the building block of everything else. Two hydrogens combining to make a helium, and then from there it kind of snowballs into all of our elements. So nuclear fusion in the sun produces energy using fusion of hydrogen. Four hydrogen nuclei combine to form one helium nucleus. We get this energy, obviously, I mean, we feel the heat energy, the radiation from the sun because of all these reactions. Small amounts of mass is changed into a large amount of energy, which we see as heat and light. So far, 1% of the sun's mass has been converted to energy, estimated to last 5 billion years. Okay, so far we've only used up 1% of the sun's mass for all the energy that the sun has given us for the recorded time that we have. Okay, so what you also might be thinking, I kind of mentioned it before, isn't it weird that in fusion and fission that the mass isn't the same before the reaction as it is after? Because I thought we had this thing called the law of conservation of mass that says whatever I start with, I have to end with. Hey, well, again, that's because that mass is being converted into energy. It's not getting rid of the mass. Okay, I'm not starting with 7 as a mass and then ending with 6. Okay, that can't happen. Okay, I have to have the same amount of mass on both sides. Okay, what it ends up being is, let's say I start with 7 and now it's 6, but then there's a plus energy on the end of that. And that's because some of the mass got converted to the energy with our E equals mc squared equation, which allows us to do that. According to the theory of special relativity by Einstein, a super large amount of energy is the same thing as a very small amount of mass. This can only be observed with huge quantities of energy like fission and fusion create. E equals mc squared is the equation we use, and I have on there what the speed of light is, and that's 3 times 10 to the 8th meters per second. So if you imagine I am squaring that number, okay, that number is 300 million meters per second, and then I'm squaring it, so 300 million times 300 million, which is a huge number. Okay, that is all I have for you for nuclear chemistry. There's going to be some other videos that kind of take you through how the nuclear bomb works, how a nuclear power plant works. Do me a favor and check those out. I don't have an assignment for you for this week just because I want you to focus on getting all your past assignments in and focusing on being ready for the final coming on Thursday. As always, thank you for watching. Thank you to those of you that have been keeping up with your work and trying to access all of the stuff that I've been posting and doing your assignments and all that stuff. I want you guys to all have a great summer. I hope to see you again in the fall. I will say to not completely get your hopes up. We could be doing online learning as well in the fall. We just really don't know right now. We'll see how the summer goes in this ever-changing whatever situation you want to call this. But as always, thanks for watching. Hope you have a great summer.